Welcome to Virtual Regeneron ISEF. I'm Emily Conover, physics reporter for Science News, a publication of the Society for Science and the Public. In this session, we'll be discussing the great physics questions that remain unanswered. With me is Brian Greene, a professor of physics and mathematics at Columbia University. He is also a renowned science communicator. He's written several books that have inspired a generation of physicists and physics enthusiasts. I think I can say that because I'm one of them. When I was in college, I read The Elegant Universe as part of my first undergraduate physics class. He also co-founded the World Science Festival, and he's an alumnus of the 1980 Science Talent Search and the 1980 ISEF. Welcome, Brian.
Thank you.
As I said, you competed in ISEF and the Science Talent Search. What was that experience like for you, and what words of encouragement would you give to the next generation of scientists and engineers?
Well, it was very exciting to work on a research project as opposed to just doing the homework assignments in the science classes. I think that shift from working on problems where you know there's an answer to working on problems where there may not be an answer is a vital and exciting step that every young scientist has to take. So being part of the competition that sort of drives you in that direction, for me, was a great experience. And, you know, in terms of advice to young students who aspire to be scientists, the advice is really this: get excited about the forefront of discovery. Get excited about, say, your own research, but don't skimp on learning the basics. You've got to get the basics of whatever science you're studying. For me, it's physics. You got to learn the basics of mechanics, the basics of quantum. You got to learn the basics of statistical mechanics. You can't skip over the old stuff just to get to the new, because the old stuff will serve you well if you master it.
Okay, well, let's get into some big physics questions. So I think one of the biggest holes, the biggest puzzles in physics is that we don't understand what most of the universe is made up of. There's these unknowns, dark matter, dark energy. Why are physicists so convinced of the existence of these shadowy elements of the universe, and what does it say about our understanding of physics that so much of the universe is unknown?
Yeah, it is kind of weird at first when you hear that something like 95% of the universe, we don't really know what it is, that the stuff that we focus upon, say, even in the science classroom, the protons, the neutrons, the quarks inside of them, the electrons, the neutrinos, depending how far your class goes, that all that familiar stuff only makes up a small percent of the mass energy of the entire universe. So yes, it does expose our ignorance of some vital qualities of reality. But the amazing thing is, even though we've learned that there's other stuff and we can't quite identify it, we do know a lot about it, and our observations and experiment have given us insight into the very existence of this other stuff. So for dark matter, back in the 30s, we learned from the motion of galaxies and stars within galaxies that there simply wasn't enough gravitational pull to account for the motion of the things that we were observing. There had to be more gravity, but there wasn't anything obviously out there that was giving rise to that gravity. But look, we can only see things that give off light. So the suggestion is maybe there's more stuff out there that we can't see because it doesn't give off light, and yet it gives rise to the gravitational pull that we see indirectly by virtue of the motion of stars and galaxies. Then in 1998, this notion of dark stuff took a dramatic leap forward when we learned that not only is space expanding, something we've known about since the late 1920s, but it's speeding up in its expansion. That's unexpected. Everyone thought that, you know, just like when you throw an apple upward, it goes up slower and slower because the Earth's gravity pulls it back. Everyone thought that the distant galaxies, yeah, they may be rushing away, but they're going to rush away slower and slower because the mutual gravitational pulls will draw them back together. But then observations showed that the distant galaxies are actually rushing away faster and faster. What's the best explanation we have today for that motion? Gravity can actually be repulsive. If gravity is not sourced by a clumpy thing like a planet or a star, but by a uniform distribution of energy, the gravitational force will push outward. So the best explanation we have is that there is some dark energy. We don't see it, doesn't give off light, it's invisible, that's permeating space, and that's the explanation for the observations. So it's a kind of weird situation. Very precise observations show us that these things exist, but trying to identify them precisely has so far eluded our investigations.
Yeah, there's a lot to be understood, which I think makes physics an exciting field. So let's go to one of the questions from our finalists. I want to make sure we get a chance to answer these because we had a bunch of great questions. So this question is from Aniko Lagi of Ann Arbor, Michigan.
My question for you guys is as follows. Suppose you're stuck on an island, and the only way you leave this island is by answering this question. Now, I know this question is almost impossible to ask a physicist, but if you had to pick one of the following differential equations to have most advanced the field of physics, which one would you pick? Number 1, Maxwell's equations. Number 2, Einstein's field equations. Number 3, the Hamilton equations. Or number 4, Schrodinger's wave equation. Thank you.
Oh, that's such a good question. What I'm not quite certain about with the question is, when I take this differential equation with me, what can I do with it? Do I have to erase the others from my mind? Because they're all in here right now. I think I would probably take them all with me. But let me just give the following as my answer. Schrodinger's equation, to me, is a triumphant equation because it is not a single equation. It is a framework of equations that allow you to understand basically any physical system by plugging in its details to the so-called Hamiltonian of the Schrodinger equation. So if I had any hope of using this equation to build new stuff, I'd want to have the Schrodinger equation with me. Maxwell's equations, look, everything we know about the world, we learn through electromagnetic radiation. So how can you not have a warm, fuzzy feeling when it comes to Maxwell's equations? What were the others now? So the Einstein field equations, I want to come to that last, but there was a fourth one in there. What am I missing? Oh, Hamilton's. The least, yeah. So if you want to understand the basic architecture of fundamental physics, then Hamilton's principle, the principle of least action, this gives you, again, the basic equations of classical physics, and in the path integral, it gives you the formalism for doing quantum mechanics. So, how can you leave that behind? And finally, Einstein's field equations, I mean, that's the crowning glory of scientific exploration. The warping and curving of space and time being the explanation for the force of gravity. Wow. So I guess I would plead with whoever was going to strand me on this desert island. I'm going to leave my clothes. I'll leave the food. I'll leave all the provisions. But come on, let me take all of those equations with me. Yeah. Yeah, I should say at the outset, it's a puzzle that we've yet to fully resolve. Again, almost like with the dark matter and the dark energy, we've gotten very good at quantifying the degree of the imbalance between matter and antimatter that we need. Roughly speaking, the early universe, for every billion particles of antimatter, we needed to have 1,000,000,001 particles of matter, so that when they collided and annihilated, there'd be one particle of matter left over for each of these billion or so collections. But where did that 1,000,001 to billion disparity, imbalance, come from? And people have been struggling with this for decades. Andrei Sakharov, great Russian physicist, wrote down a series of conditions on any theory in order for it to have a chance of explaining this imbalance. And a key part of the criteria that he wrote down is there has to be something in the fundamental equations that distinguishes between matter and antimatter. If the math treats them exactly the same way, and the math is correct in its description of the physical universe, it's very hard to see how an imbalance could ever possibly form. So there's something called CP violation. C stands for charge conjugation, P for parity. Charge conjugation, that's the easy one. Change a plus charge to a minus to a plus. So that changes an electron to a positron, its antimatter cousin. And you have to have a violation of these symmetries. And we've searched for such violations. There is a subtle violation in a system called the kaon system. Most people do not believe that that's really adequate, say. There is a potential violation in the neutrino system, certain so-called mixing angles between different families of neutrinos, the electron, the muon, the tau neutrino. And that seems to be a very promising possibility. Recent work out of Japan suggests that this asymmetry may have been measured. So it's work in progress. It's a vital question. There are ideas that are being pursued, but the jury's still out on what the final answer will be on how matter and antimatter got into this slight imbalance, allowing us to exist.
Right. Okay. Well, let's hear from another finalist. This is Gokul Kupusamy of Sydney, Australia.
My question for the panel is, how do you think the universe happened to be so beautifully balanced that life can exist?
Well, that's another tough one. Of course, some people look beyond science for an answer to that kind of question. Maybe one day we'll be forced to do that. I don't think so. I think that our understanding of the fundamental laws and processes will ultimately give us an explanation for how life can form on at least one planet. Key to it is an understanding of evolution. And I don't just mean evolution in the way that, say, Darwin discussed it, the way we often discuss it in an introductory biology class. Natural selection and evolution go way back, even well before the emergence of life. Even at the level of particles, molecules, there's a kind of natural selection that can kick in where the process can refine the molecular structures. When molecules learn one trick, the ability to replicate, make copies of themselves, then you recognize that those molecules that can replicate faster, swifter, more economically, greater stability, they're going to win in a kind of chemical combat that we believe took place in the early stages of, say, planet Earth. And that kind of competition for the raw material, the molecules and atoms in the environment, can yield molecules that are ever better structured, ever better able to survive in the environment that they inhabit. They're not alive yet, but you can see that the progression of this kind of molecular Darwinism can yield the refined structures necessary for cells, necessary for life. So filling in all the details is something that science has not yet done, but at least we can see the framework by which collections of atoms can coalesce into more complex structures that ultimately can yield those necessary for life. So you guys are going to have to fill in the details, but my belief and the belief of many scientists is that science will ultimately be up to the challenge. You don't need to go beyond science to answer this question. At least I don't think you do.
Great. Okay. Let's go to another sort of exciting topic in physics right now, which is the study of gravitational waves. So these are ripples in space-time that we've just recently been able to detect. And I'm curious what you're most looking forward to learning from these experiments and what kind of big questions you think we might be able to answer in the future.
Well, it's hugely exciting, of course, not only because Einstein's theory came through once again. I mean, Einstein was a pretty smart fellow, and even the ideas that didn't seem testable when they first emerged from his theory 100 years ago, now they're not only tested, but being used to observe the universe in a new way. And we certainly have ample evidence from the past that every time we can look at the cosmos in a different way, right? With our eyes, we look with visible light, then we build devices that can examine the universe in the X-ray, the infrared, gamma ray, and then we move away even from electromagnetic radiation to gravitational radiation, and we're looking at the universe with fresh eyes. So what do I hope that we will find or see? Look, the real answer to that question is, I hope we'll find things that we couldn't possibly have imagined by virtue of our intuition based on examining the universe with electromagnetic radiation, what we have done since we first looked skyward. But being a little bit more specific, gravitational waves have the potential to penetrate into realms that light cannot. And in the dream, the fantasy, the best of all worlds, maybe one day we'll use gravitational radiation to peer back through the cosmic microwave background radiation, which in the early universe is just too thick, right? There's a plasma of particles, charged particles there, that prevents light from emerging. Light can only emerge about 380,000 years after the Big Bang. We'd like to look further back than that. Gravitational waves in principle can do that. So maybe one day we will use gravitational waves to look at the Big Bang itself. That would be pretty stunning.
Yeah, very exciting. Great. Okay, so another finalist question comes from Asil Bukhari from Dhahran, Saudi Arabia.
My question to the panel is, how close have we come to developing a unified theory of quantum gravity? Thank you.
Well, it depends who you ask. I have a biased opinion, perhaps. No, I think I actually have a pretty balanced opinion. On paper, we have a theory, string theory, M theory, whatever name you want to give it, that does appear to put gravity and quantum mechanics together into a consistent mathematical formalism. And that's enormously exciting, and that's why many people have and continue to work on this theory. But the question really is this just a mathematical union of gravity and quantum mechanics giving us this unification, or is it a theory that describes our universe? Those are two separate questions. Gravity and quantum mechanics could be melded in a mathematical formalism that's self-consistent, but it has nothing to do with how gravity and quantum mechanics are melded in the world around us. So we need observation and experiment to tell us whether string theory is correct, and we've yet to achieve that goal. The hope is that the Large Hadron Collider might give us some evidence of that sort. It has not. That does not rule string theory out. And by the way, I'd be thrilled if it did rule string theory out. I'm not wedded to any approach. If string theory is not correct, I do think you could go around once in this life, and I'd rather not spend any more time on it if we could prove that it's wrong. But rather, the experiments establish that the machines that we currently have at our disposal may not have adequate intensity and energy to test the exotic physics that comes out of string theory. So we're left kind of hanging a little bit up in the air. Are there other approaches? Competitors? Sure. Loop quantum gravity is an approach that people work on, and I'm glad that they do. It's an approach that may well be the right one. I, of course, personally don't think that it is, or else I would be working on that approach as opposed to string theory. But part of the health of a field is evidenced by the distinct ideas that people have for pursuing solutions. So I'm glad that there are competitive approaches that people are working on. And it's very hard to say when or if these ideas will be established as the right unified theory.
Great. Yeah, it's a lot to think about, a lot to leave future generations to work on.
Without a doubt.
Great. Okay, so let's talk about a conundrum that I know a lot of physicists have been puzzling over, which is what happens to information that falls into a black hole? Is it destroyed, and why is this such an important question?
Well, it's a real important question because when you look at the laws of quantum mechanics, you see that the laws, for them to make sense, require that there's no loss of information in the universe. What does that really mean? Well, it's not a tricky idea. If you want to make predictions about what will happen in the future, which is what physics is all about, even if those predictions are probabilistic, as they are in quantum mechanics, you can't lose information along the way. A loss of information along the way would fundamentally compromise your ability to make predictions. And in fact, mathematically, the incarnation of that loss of information would be a loss of all of the essential qualities of Schrodinger's equation that we discussed earlier that have allowed us to have confidence that it is a good description of the physical world. And the culprit for the loss of information, as you mentioned, are black holes. Stephen Hawking gave us insights into black holes in 1974, which helped us. I mean, if stuff falls into a black hole, you'd say, well, maybe the information's not gone, it's just locked inside. It's like in a briefcase and you put a lock on it, and you threw it to the side, maybe even lose the briefcase, but it's still somewhere in the world. It's not really lost. But when Hawking came along and showed us that black holes can radiate, they can give back the energy that they swallowed, but his math seemed to suggest that the radiation would contain no information. So it's as if the black hole gives back everything it went in, but it destroys the information in the process. That would be no good. That would be like that suitcase truly disappearing because the information that it contained would no longer be accessible. So we've been struggling ever since. And I would say that the state of the art is most people, even Stephen Hawking before he passed away, changed his perspective. He thought that information was just lost, period, end of story, get used to it, own up to it. But string theorists, quantum gravity people were not that willing to give up the beauties of quantum mechanics, which this would require. And people like Leonard Susskind and Gerard 't Hooft and many string theorists were able to come up with proposals for how the information is not lost, for how the information may actually secretly come out of a black hole. And I'd say that's the perspective that most people have, but the story's not yet fully written. Twists in the tale have come along in the last 2 years where people have wondered about the details of something known as quantum entanglement, when the particles are linked by threads of quantum connection that may span right across the edge of a black hole. What happens? This leads us to the possibility that there might be a firewall on the edge of a black hole where when something falls in, it gets incinerated. There may not even be an inside to the black hole. The edge, that firewall, that hot surface might be the end of space itself. These are questions that people are still vigorously pursuing, but I think most of us are comfortable predicting that when the dust settles, the information will not be lost.
Okay, great. So another question from a finalist, Neil Kadian from Jersey City, New Jersey asks,
if consciousness can be explained entirely by physical phenomena, does that mean we are deterministic beings? And if so, what implications does determinism have in the way we make choices in our lives?
Well, determinism is a interesting word. You have to be very careful what you mean by it. Some people, by determinism, means that the past fully determines what will happen in the future in the sense of Newtonian classical mechanics. Tell me where the particles are now, use Newton's equations to tell me where the particles will be tomorrow. The world doesn't operate that way. It operates by the laws of quantum mechanics. But the math of quantum mechanics is deterministic in the sense that you tell me the probabilities of where things are today, and the math tells you the probabilities of where they will be tomorrow. So it's just as deterministic, but it determines probabilities as opposed to definite outcomes. And in that notion of determinism, then yeah, we are deterministic beings. My view, as I discuss in my book, and I believe that must be where this question is coming from, in a book called Until the End of Time, one of the chapters takes on consciousness. And in that book, I describe the view, which I hold to firmly, that everything we think, everything we do, everything that emanates from our bodily form is fully determined by the motion of our particles. We are collections of particles governed, say, by the quantum laws of physics. And there's no opportunity for any of us to intercede in that mathematical unfolding. And therefore, the particles, whether they're in a particle collider or inside a human body, are still governed by the same quantum mechanical progression. And therefore, there's no chance for us, a human being, to step in and say, hold on, laws, take a break for just a second, wait for me to make a decision. And after I've made my decision, you can then carry out my marching orders. That's not how the world works. Particles have quantum mechanical marching orders. They never stop functioning. They never stop controlling the evolution. So yes, in that sense, we do not have free will in the traditional sense that we are the ultimate authors of our actions. What implications does this have? Well, it has a lot of implications, but I think the one that naturally comes to mind is, are you responsible for your actions if you don't freely will them? And my answer to that is absolutely yes. Anything that you do, anything that your particles do, you are responsible for because you are your particles, period, end of story. The second question, though, is should you be punished for things, say, that society deems you should not have done? The answer to that, again, is quite straightforward. Punishment as retribution, I don't see any place for. Punishment as a means of affecting the future behavior of past collections of particles, yeah, punishment can help mold future behaviors. Objects do not need free will to learn. A Roomba, it learns where my furniture is in my apartment every time it cleans the floor. It's got no free will, but it learns. It does better the second time than the first. And therefore, non-free-willed entities can learn. And if by punishing some of those entities for their actions, you can instruct that collection of particles or others, then there's a role for punishment. So yes, I could go on forever on this, but we don't have much more time, so I'll stop there. But it's a good question. More details, you should check out that chapter, or send me an email. But this is a question I'm deeply interested in.
Okay, great. Well, I wanted to ask you a little bit of a personal question. So you obviously spend a lot of your time working to share science with the public. Why is that such a priority for you?
Well, I consider science to not be a subject in a classroom. It's not a major that you choose in college. I consider science to be an integral part of how you have a full life. And the tragedy is so many people who would be interested in the insights of science are cut off from those insights because we frame them in a very specific esoteric language, the language of mathematics, the language of various of the sciences that has technical jargon. So I've seen my role partly for a long time, as you do as well, to try to be a bridge between the technical things that we do, say, in the laboratory and the research environment, and bring those out so that everybody can enjoy the most exciting discovery that the species has been traversing, this trek toward truth. That's something that everybody should have access to. And the work that I do and science journalists like yourself do is an important part of making those discoveries available.
Okay, great. And I'm just curious how you deal with any setbacks in your work. Do you have any advice for young scientists who might have to work through difficult problems?
Yes. So thankfully, I've never had a setback. Anything? No. I mean, we have setbacks all the time. In fact, I'm fond of telling my students that 99.9% of what we do is wrong. I'm not saying wrong like we made a mistake. Sometimes we do make mistakes. Hopefully you correct those. But by wrong, I mean, even if the math is correct, what we do may not be relevant to how the world works, like string theory, decades of work in that, but other things too. You look in the journals, most papers, even if they're interesting, they don't have direct relevance to the world because the world is one specific way, and we are hunting around in the dark to try to find the right language, the right equations to express the patterns of reality. So expect to be wrong most of the time, And therefore, enjoy the exploration, enjoy the journey. Being right in the sense of actually describing reality, that is kind of the icing on the cake, at least if you are working on fundamental physics. So enjoy the ride as opposed to just the fruits of the major successes.
Great. Okay, well, I think that's it for our session. Thanks to Brian Green for joining us at Virtual Regeneron ISEF, and thanks for sharing your deep insights with us.
Thank you.